Fatigue test. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with two half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals two regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. The first specimen was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used.